is a postdoc at the CS department in CERIAS.
Good afternoon, and thank you, Professor Bertina, for the introduction. Today I will present a paper on private queries in location-based services. This work has been presented earlier this year at the ACM SIGMOD conference in Vancouver. I will first give a brief outline of the talk. So what will be covered? I will first give a brief overview of privacy in location-based services. Then I will review some of the existing solutions that solve this problem. Most of the solutions will use spatial cloaking, and this is the reason why they have certain limitations, which I will discuss. And then I will move on to present our technique, which is different from existing solutions because it uses cryptography to solve this problem. And more specifically, we use private information retrieval, or PIR. I will try to stop every few slides so we can answer any questions that may arise. And I have also included slide numbers if you want to refer to a particular slide. So moving on to the location-based services, or LBS overview. The users of location-based services have mobile devices, and these devices are GPS enabled. The users are able to ask queries which are relative to their location, for instance, nearest neighbor queries. We have here an example with a number of users shown as dots and a number of points of interest. In this case, we have hospitals age 1 to age 5. In our example, we have user U1 who has the query, find the closest hospital to my present location. This query can be answered in a public location server, for instance, Google Maps, which stores the points of interest. However, the location server is not trusted. And in addition to that, we may have some malicious attacker which intercepts the query from the user to the server, and the attacker can infer that U1, for instance, may suffer from a medical condition. And this is a violation of the user privacy. We want to prevent that. One immediate solution is to have U1 remove his identity from the query. So instead of sending the exact identity of the user will use a pseudonym service or anonymous web surfing service. There are a lot of those services nowadays. But there is still a problem. In order to process the query and return a meaningful result, the query must contain the location of the user. And this location can be mapped to the user identity, for instance, using signal triangulation, or even with more simple methods. If, for instance, the user issues this query from its residence, then it is very simple to look for this address in a public telephone directory and we can find out who the user was. So the problem that we're trying to solve is how can we still provide these location-based services, and at the same time we want to preserve the anonymity of the query source. And there are a number of techniques that have been proposed so far. Most of them rely on the spatial k-anonymity concept. K-anonymity is a concept borrowed from relational databases. And the idea is that the query issuer is hidden among other k-1 users. And therefore, the probability of identifying some individual user is bounded above by 1 over k. How can we do this for spatial k-anonymity? The idea is to build a cloaking region, or an ASR, we call it, an anonymizing spatial region, which will enclose the location of at least k users. So revisiting our example, again we have U1 asking the same query. It's just that this time, instead of sending the exact location of the user to the server, first there is this rectangle, this ASR, which is built. In this case, we consider the value of parameter k to be equals to 3. And we have a 3 ASR. The server will process the query with respect to this ASR. And because of that, a number of redundant results will be included in the response. Why? Because in addition to H2, which is the actual answer, there are also hospitals H3 and H4, which are candidate or potential nearest neighbors of some point which lies within the region. And enlarging the exact location to a region adds some additional overhead for the query processing. And there is another factor. there may be some financial cost or billing cost associated to this enlargement. Why? Because we can see here that we send 3 times as many results as in the case of the point query. And if the user is billed with the amount, with respect to the amount of the results returned, then this will result in an increase in cost. I will come back to this issue later in the talk when we will compare with existing solutions, and I'll discuss more about the financial cost involved. Now that we have an idea of how to achieve anonymity, we see that there are a few elements here. We need, for instance, to know the location of other users. So how can we enforce this privacy paradigm? Most solutions use this architecture. It's a 3-tier architecture. On the left-hand side, we have the users with mobile devices. On the right-hand side, we have the location server. In the middle, we have the anonymizer service. I will just refer to this as anonymizer so we don't confuse it with the location server. What happens is that users will subscribe to this anonymizer service. And then each user has to periodically update the location where he's situated. Whenever a query is sent, instead of sending the query directly to the location server, we will send it first to the anonymizer. The anonymizer will assemble the ASR, as we have seen in the previous example. Then the ASR is sent to the location server. The location server will process the query, send back the candidate results, which, as I mentioned earlier, are a superset of the actual result. And then the anonymizer will filter the result and send back the actual result to the user. There are a few obvious flaws with this architecture. First of all, we have a single point of attack. If somebody breaks into the anonymizer, everybody's privacy is compromised. And another problem is a performance problem, because all the queries and all the updates of locations must go through this server. Therefore, there would be a performance problem, right? A bottleneck. I will now move on to discuss specifically, so we have seen the architecture that is used, and I will discuss specifically a few methods, and we will only look at the part which happens at the anonymizer. So we want to know exactly how the ASRs are built. The first paper that I'm going to introduce is Casper, the first method. This is a VLDB 206 paper. The idea is to store all the user locations in a spatial index. In this case, a quadtree index is used. The quadtree is a very simple spatial structure which partitions the space into 4 quarters, 4 quadrants. And this is recursively performed until some condition is met. For instance, every quadrant contains at most 1 user, or some other number of users which fit in a disk page. How is anonymization performed? Whenever a query arrives at the anonymizer, the algorithm will search for the lowest level quadrant in the tree, which contains the query source, as well as k-1 other users. So this is performed in a bottom-up fashion. And let's see an example. Again, let's assume k equals to 3. And maybe let's assume that U1 or any of U1, U2, or U3 issues a query. According to the algorithm that we have just described, the solution will be, or the cloaked region obtained will be A1, the red rectangle. Now, if a query is issued by U4 with the same parameter k, we will obtain the A2 region, which is obviously larger. Now, if an attacker has some knowledge on the distribution of locations, so he doesn't even need to know the exact locations. All we need to know as an attacker is the distribution of locations. Then, by simply looking at the size of the generated ASR, the attacker might see that U4 must have been the query source, right? So this method exposes the privacy of the outliers. How can we deal with this? After Casper, there was another method proposed which talked about the concept of reciprocity. This is actually also our paper. It's a TKD 207 paper. So this property, which in retrospect seems pretty simple, says that whenever some user UI generates an ASR, and that ASR includes some user UJ, then the reciprocal must occur. Here in this example, whenever U2, U3, or U5 issue a query, we will have the associated ASR. And similarly, whenever U1, U4, or U6 issue a query, a different ASR. So the challenge here is that we need to partition the set of users into disjoint sets. Each set must have at least k users. And also we have an optimization goal of minimizing the sum of ASR areas, right? Why? Intuitively, the cost of the query processing is proportional to the area. So the solution proposed was an heuristic. This problem is NP-hard, even in 2 dimensions, right? Finding an optimal solution. So the heuristic proposed was based on fractals, dimensionality mapping. Are you familiar with the Hilbert fractal? So just a few words. This is not the main topic of this talk. So we have a 2-dimensional space. We split this space according to a regular grid. And then there is this curve, which is defined recursively. We can have various levels of granularity. The idea is that this curve traverses each cell of the space exactly once. And the order of the traversal gives an integer, a number for each cell. When a location falls within a particular cell, it has that associated number. For instance, this cell would be number 8, right? To have another example, a sample distribution of users will be mapped probably to something like this. And then within the sequence, we can simply split the 1D sequence into blocks of users of at least k. And this will determine the generated cloaking regions. This method works well if users are stationary. But that's not the case to happen in practice. Most of the time, users will move. And if the users will move, the sequence will change. If a user issues a continuous query, which means that the same query is generated at multiple timestamps from different locations. For instance, if I travel in my car and I want to have a constantly updated list of what is the nearest restaurant to my location, right? Let's say that I will post such a query, and then the server will send me back every minute the new set of results, which will change. Because I will change my location and I will appear in each ASR, it will be very easy for an attacker to do a simple intersection and see I must be the query source. So this method does not work for continuous queries. There was another method, and this is the last related work method that I will present. This was an SSTD 207 paper, which proposed the following simple fix. We can take the first snapshot of the continuous query and apply any reciprocal method on top of that, for instance, Hilbert cloak. Then we freeze this set of users, and at the next timestamp, when the users will move, we will get a new ASR, which is their bounding rectangle. Obviously, there are 2 problems here. The first problem is that this rectangle will grow very large if the users will move in different directions. So maybe this would end up to be the entire data space. This is not practical. And the other problem is that if at least one user in the initial set will drop or disconnect, then the privacy of all other users is compromised, right? So with all these things discussed, can anybody help me summarize what are the motivations behind our work? Why do we want to have a new method? So what are the problems that we have seen? No? Yeah.
Anonymity, law and move.
Okay, so handling continuous queries, right? Privacy for continuous queries. This would be one factor, right? So existing methods cannot achieve privacy. Something else? I'm sorry? Okay, so that would be minimizing the regions, right? Okay, very good point.
If there are few users or one user, how to protect a single user in such case?
Well, yes, there's a very good point. So we assume that the query is not issued if there are not enough users. We can protect against that. But you made a very good point, because there is a business model here that must be, in the end, sustained. And I will formulate it as considerable overhead for sporadic benefits. If I ask a query once a week, but I have to report my location every minute, such that other people can ask queries, would I really want to do that? Right? So this is one problem. The other problem is that in order to have these ASRs at a decent level of extent, we're going to need a lot of users. So we're going to need a high user density, right? And where are we going to get all these users from? Can we pool as a service provider, can an anonymizer subscribe so many users so this method gets to be usable? Another problem, very important, there are a lot of assumptions on trusted entities. We assume that the anonymizer is trusted. That's fine, but what if it gets broken into? Furthermore, it is a bottleneck of performance, right? Then we assume that we have non-colluding users. But what if some attacker will subscribe with 1,000 users, fake users, decoys, and will upload some bogus locations distributed all over the data space? Whenever the attacker will intercept an ASR, he can filter out those users, and then he exposes the actual query source, right? So this is a fundamental problem regardless of the geometrical transformation that we use. So the questions that we want to ask is, can we have privacy, provable privacy for continuous queries? And if we do this, can we do it in such a way that we do not need to rely on other users? And if we can do that, can we do it in such a way that we don't need a centralized component? And there is another point here, and a very delicate point. Anybody want to make a guess? We discussed about this K anonymity. What about K? Do you think that this is convincing enough? What should we set K to? Is it 10? Is it 100? What is enough privacy? How can we define enough privacy? And then there is the trade-off. The larger the K, the larger the size of the SR, the more overhead. So can we achieve all these tasks and at the same time have some privacy, let's say, measurement which does not depend on any parameter? And instead we could have something as follows. All the attacker must find out is that I must have a mobile phone with a GPS device. This is definitely a stronger privacy guarantee, right? So can we do this? And we believe we can. And I will move on to discuss our technique. But before that, if there are any questions so far. Okay, I guess we can carry on. So as I mentioned earlier, we do not use spatial cloaking. We use cryptography. In particular, we use private information retrieval, or PIR. So let's see how PIR works in a nutshell. We have on the right-hand side the server, a generic server. In our case, it's the LBS server, but for this particular case, we assume some very simple data format, a binary string, X, with elements x1 to xn. On the left-hand side, we have a client. This is a two-tier architecture. There is no intermediate anonymizer. So what Bob wants, the client, he wants to retrieve the item xi. Okay, so the search is based on index. However, he does not want the server to find out the value of I. So what is he going to do? He's going to encrypt this value of I, and I'm going to use the term encryption, although strictly speaking it's not encryption because there is no associated decryption, but I'm just going to use the term encryption. We can assume here that we say hidden. So it encrypts this I index into a query key of I, and this query is sent to the server. It is computationally hard for the server to determine the value of I based on Q of I, right? What the server will do will process the query and will return a function which is the result R, a function of the entire dataset X and Q of I. And based on this result, Bob can easily find Xi, the value of Xi, and this is done using the trapdoor function. I will show shortly how. A few mathematical properties. I will just skip very briefly over these. So the PI protocol that we are using relies on the assumption that it's difficult to find out whether certain large numbers have a certain property. And the setting is the following. We have two large primes. This is similar to if you want the RSA setting, right? Standard encryption. We have their product n. And then we have the set QR. QR is the set of quadratic residues. And it consists of those numbers which are prime to n, and also have the property that there exists another x, so the numbers y in which are prime to n, and for which there exists x, such that y equals x squared in modular arithmetic. And based on this definition, we can define the complement, right, which is the QNR set. The numbers which are not in this set, which are not quadratic residues and are quadratic non-residues. The quadratic residue is the assumption QRA states that it is difficult, it is computationally hard to decide whether a number, a given number, with n bits is a QR or a QNR if the factorization is not known. And the number is situated in this Zn plus 1 set. This is a restriction of the set of Zn. I will not go into details because we don't really need these details. All we need to know is that there are two essential properties. If we multiply two QR numbers, we obtain a QR. So a QR times a QR is a QR. A QR multiplied with a QNR is a QNR. So this is what we need to know for the protocol. What about if we multiply a QNR with a QNR? What happens? What are we going to get? A square? Any other opinions? Sometimes we get a square, sometimes not, right? So the answer is maybe. Sometimes we get a QR, sometimes we get a QNR. But fortunately, we don't use this in the protocol ever, so we don't have to worry, because we're only going to use these two operations, right? So how does the protocol work for binary data? We have again the X string. This is stored at the server, right? We organize the data into a rectangular matrix. So it's the same data that we had previously, right? Each element is a bit. Now, some client wants to retrieve, let's say, the value of x10. The client will also know the geometry of the matrix. He knows how many columns and rows are. So he can determine the row and the column, right? Row is A equals to 2 and B equals to 3. Indices here start from 1. What is the user going to do? He's going to generate the query that we have seen. And this query is an array of numbers, y. Each y number is an n-bit number, right? Is a large number. Out of these numbers, we randomly generated, we make sure that y3 is a QNR. All the rest are quadratic residues. This query is sent to the server. Because the server does not know the factorization, he doesn't know which one of the numbers is a QNR and which one is a QR, right? What is the server going to do? For each row of the database of the matrix, it will multiply those y numbers for which the corresponding x value is 1. Okay? So it's some sort of a masked, if you like, a masked product. Only those elements in y which correspond to 1 values in the matrix are multiplied, right? So at the end of this protocol, each z value will store the products of the y value corresponding to the ones in the matrix. This is captured here with this complicated and useless formula. Now, what we need to know is that if the value of all these results are sent back to the user, right? We have Z1 to Z4. Why do we need to send them all? Because the server does not know in which row the element searched was in. So we have to send all this back to the user. The user will look at the value of Z2 and decide if Z2 is a QNR, then X10 must have been 1. If Z2 is a QR, then it must have been 0. Is it clear why? So the intuition is the following. The only way I could have obtained a QNR is if Y3 is included in the product, right? We have seen earlier that if I multiply 2 QRs, I only get QR. So the only way for this Z to have been to be a QNR is if Y3 was included in the product. And Y3 is included in the product for the corresponding row only if X10 would have been 1, right? Questions? Okay. So there are a few things here to highlight. First, we have some sort of redundancy in the result that is being sent. We have seen that we had that redundancy for spatial method as well. We will see how to make use of this redundancy. Second, this works for binary data. However, if we want to have objects which consist of multiple bits, we can simply imagine that we have another dimension, right? Orthogonal to the board, a depth of this matrix. And the object the multi-bit object will be stored in this depth, right? So what's going to happen is that instead of using the operation on bits, as we did in this protocol, we can simply have a protocol which works at the level of memory words, if you like. This is maybe a good comparison. So when we operate with memory words, we perform the operation on each bit, right? So this would be how the method works for multiple bits. Now, this is the generic PIR protocol. Now I'll show how we apply this to our problem. First, I will consider approximate queries, approximate nearest neighbor queries. We have here a number of points of interest. So from this point forward, all the points that we will have in the diagrams are points of interest. There are no other users, right? There are no index, no locations of users known. The server does not know location of users. So these are the points of interest. And the idea is the following. Based on this data set of locations, we built a spatial index. This spatial index can be anything ranging from a KD tree, maybe a code tree, or code tree is unlikely, an R tree is more likely. With the following properties. In each leaf node, we must have at most square root of n elements, where n is the number of POIs. And the other condition is that the tree must have two levels. And it is easy to show that no matter what structure we use, some broad tree that we use, we can achieve these conditions. For instance, here we have a KD tree. The idea behind the KD tree is to split the space recursively until in each partition we have a limited number of users. So for instance, here we have first a split along the one axis, which gives us a partition of 3 and a large partition of 6, which is further partitioned into B and C, each of them having 3 points. This is done one time. This is a pre-processing of the data set. What happens when the user issues a query? Okay, one more step, which is important. So based on this data index, how do we build the PIR metrics that we have seen earlier? Simply by storing each leaf node into a column, right? And because of the cardinality condition, we can always do this. So the P1, P2, P3 leaf node will be stored in this column, right? Similarly for the other leaf nodes. When a user issues a query, first the user will retrieve the root node. This can be accessed in plain text. We don't need any encryption, right? Why is that? The root node corresponds to the entire space, right? So no matter where I am, I would still ask for the root node. So this is a protocol which is performed by every user in the system. So based on the fact that I ask the root node as a user, I don't give away any information, right? Because all the users do the same. Once I find out what the root node is, so basically I would know the rectangles A, B, and C, I will see where I am myself. And let's assume that I am in leaf C. Then what I will do, I will perform a protocol, a private information retrieval protocol, only for this column here. And this time, I will use all of the elements that are retrieved. And this is why I said that we can make use of this redundancy. So what we will do, we will bring all the elements in leaf C, P1, P2, and P3. And then the user can choose which one is the nearest. Of course, this is still approximate. If the user, for instance, would be situated somewhere around here, most likely the nearest neighbor will be P6 or P7. However, this gives good result in practice. Questions so far? Yes? First of all, there are no ASRs here. So ASRs, when we talk about ASRs, we talk about minimum boundary rectangles of users. This is just a simple partitioning and indexing of a set of points of interest. No, this is exactly what I was pointing out. There are no users here. But it's good that you pointed this out. So there are no users here. All these points here are points of interest. In our method, we do not have extra users to rely on. All users perform the protocol on their own. What we have here are points of interest. And these are stored at the index at the location server in such a way that the client can retrieve them in an efficient fashion. But there are no users here. All of these are hospitals, if you like.
So the points of interest are more like access points from where the user will actually access.
I'm sorry?
The points of interest are more like access points from where the user will actually access. Or are there
No, are the points that he's looking for. The points he's looking for, the landmarks that he's looking for. The user location there is in red. Only the user knows his location. The server does not know the location of the user. However, the server knows the location of all hospitals. Right? So the user will enter this protocol with the server, whereas the server will send back to the user only the points in the partition of the user, but without knowing where the user is in. Because he uses that protocol that we have seen, which hides the value of the objects that I'm looking for. So we have seen how we can do approximate queries. Can we do exact? Yes, but slightly more expensive. How? Again, assume a data space with points of interest. Given this data space, the server will partition the points according to a Voronoi diagram. And again, this is done offline. What is a Voronoi diagram? A Voronoi diagram is a disjoint partitioning of the space into polygonal regions. And the very useful property of this concept is that within each polygonal region, the points situated in this gray region are closer to P1 than to any other point in the dataset. So if I have a query point lying in this region, its actual nearest neighbor will be P1. And similarly for the other partitions.
I have a question.
Yep.
How complex is to generate the Voronoi?
Voronoi diagrams, there is a lot of literature on this, and in the spatial databases literature, and a lot of papers, and it is not difficult to generate. So for a data set of that we have used of maybe 100,000, it takes maybe less than a minute. And this is done offline. This is not done online. For 2D, for two-dimensional data set, Voronoi are very efficient. On top of this disjoint partitioning, we superimpose the regular grid. And this regular grid will correspond to the PIR matrix that we have. However, this time, we'll not have the property that we have one point of interest in each cell. Instead, what we store in each grid cell would be the points whose corresponding Voronoi cells intersect that grid cell. So let's take an example here. Cell A3 lies at the intersection of the three Voronoi diagrams corresponding to P1, P2, and P3. So we store all these points. On the other hand, inside A4, there is only the Voronoi diagram of P1, right, which is included. So we will only store P1. This is repeated for all grid cells. What is the idea? The idea is that if I retrieve the contents of a particular grid cell, I know my nearest neighbor, as long as I lie within that grid cell. So at query time, the user, assuming that he's situated in this location, will create this query. Of course, the user knows the granularity of the grid, but this is a very simple protocol there is a very simple method to find out. He can simply ask for the granularity of the grid, just like he asked for the root node in the previous example. So once he knows the granularity of the grid, the user knows his cell. He knows his column, and therefore he will ask for the corresponding D column, right? He will get the Z values that result from the protocol, and this time he will not make use of the redundancy. Why? Because this is an exact protocol. So he only needs Z2. He doesn't need the rest. And we have an optimization in the paper, which I will not discuss today, which allows us to change the geometry of the matrix. So if I decrease the number of rows, I have less redundant content, right? Any questions?
So in this case, only Z2 is returned to the...
In this case, all of them are returned because all of them. But what we can do is that we can decrease the number of rows, and fewer Z will be returned to the user.
Then if you decrease the number of rows, wouldn't the server know the rows where
Yes, but as long as all the numbers will be, if there is one single row, then the server will know that it's in that row, but all the data elements will be there as well. So from the server's point of view,
He will return all the
he processes all the cells.
yeah.
So he doesn't know in which row the data lies in. So we have seen the protocols. Now, we have also seen that each query processing involves a large number of multiplications with large numbers. Okay? A large amount of multiplications with large numbers. And the problem is that this can be costly. So, previous to our work, there were concerns that this method is not applicable in practice because it's too expensive. And actually, there was a paper which said that why don't we just download the entire database? Because at some point, we might end up cheaper. The idea is that if you are a service provider, you're not likely that you're going to want to surrender your database to a user. You're just going to want to charge the user for every access, right? So you cannot charge the user for getting the entire database. So again, there is a business model problem. However, we were able to reduce the cost of this PIR protocol, and this is also our contribution. So the PIR protocol per se is not a contribution, the PIR protocol for binary data. However, we do contribute some optimizations, and I will just briefly go through them. First, we have here a sample data matrix. We have seen earlier that we are only interested in those elements which have 1 values, right? So, for Z1, for instance, we will multiply Y3 with Y4, Y5, and Y6. This will be the result, correct? Z2 will be Y1 times Y3 times Y5 times Y6, and so on. Now, if I see that a lot of these patterns are frequent, I can save some multiplications. Why? Because using, for instance, the shaded pattern here, Y3, Y5, Y6, I can determine Z1 by multiplying this with Y4, and I can determine Z2 by multiplying with Y1. So there is a significant saving in terms of multiplications. How can we find these patterns? We can employ a data mining algorithm. Again, this is offline. As long as the data set is static, this can be quite efficient. So in an offline phase, we mine for frequent patterns of 1s. Let's assume that we found these patterns, for instance, column 2 and 3, okay, which appears 3 times, and 3, 5, 6, again 3 times. Once we identify these frequent products, we can build an execution plan, which is similar to what is happening in databases with indexes, right? So in this execution plan, whenever I want to compute Z1, I'll first check this Y3, Y5, Y6 value. If it is computed already, I use it. If not, I compute it and I cache it, and I will use it later. And we'll see that we can have significant savings. So even if the method is expensive in its original theoretical formulation, which says that you have to multiply n numbers, because basically you have to multiply all the numbers in your matrix, in practice you can save a lot. And finally, I will use the same diagram for the final optimization. So most of you probably already noticed that each row is computed independently, right? So why don't I just use parallelization? And this is an embarrassingly parallel problem. It is very easy to have linear speedup. So what we can do is that we can split horizontally this matrix, and we can send sets of rows, chunks of rows, to different CPUs. Each CPU will compute its share, will determine its Z, and return the Z, if you like, to a master, if we use a master-slave paradigm. So we can use this master-slave paradigm. In an offline phase, the master will scatter the PIR matrix in chunks of rows, and then at query time, the query is processed in parallel. And we will see again that the improvement is almost linear to the number of CPUs. Any questions so far? I'll just have to go through the experiments, and then hopefully I'll be done in time. Okay, for the experiments we have used both real and synthetic data sets. I will only present the results with real data. We have used modulus bits. By modulus I mean that n number, that large n, which is the product of primes, which again is similar to what you have in an RSA key. And let's see what we have obtained. In terms of parallel execution, the method, sequential method, is quite expensive indeed, especially for the exact AND method. But the speedup is really very good. So for instance, for the exact method, if we use a 768-bit key, the answer there is 1 second. It takes 1 second to process a query, which can be comparable to what would be done for a spatial counterpart of the query on the actual data, right? In plain text, without any PIR. This is the result obtained for using the data mining approach. So the empty elements, either dots or squares and triangles, correspond to the non-optimized run. The full points are optimized runs. So we can see that we can get as much as 50% savings, right, by employing this optimization. And if the data is static, then this can be a very good solution. By the way, all the experiments, including the parallel one, were run on standard hardware that you can find in a university. There was no special purpose machine. In practice, these operations can be very easily and efficiently implemented in a specialized machine with a very long word, for instance, which can do multiplications, because we only need to do multiplications, a very specialized operation. And this can be done with an FPGA much faster, right? And finally, comparison with previous methods on spatial transformation. First of all, I would say that there is no comparison because the assumptions are completely different, right? So we do not need a centralized component. We do not need other users. We do not need a specification of the value of k. However, we still have something to compare with, right? Because we can compare the financial cost of the two methods. And I come back to what I was saying at the beginning of the talk. The financial cost can be measured by the number of results that are being returned. Both the methods return redundant results. Okay, we have seen that. How many redundant results? The blue and red lines are our methods. The exact method returns, in this particular scenario where we have 65,000 plus points of interest, returns around 15 points of interest. The approximate method is slightly worse, around 200. But look at how many redundant points the Hilbert-Cloak method, which uses spatial generalization, is returning. And look at the population sizes. So the generalization, the spatial cloaking methods are as good as our worst method only for 64,000 users. And 64,000 subscribers might not be that easy. And furthermore, we have used k equals to 20, which is, I would say, a mild privacy constraint. Maybe I will not be very happy if I can be distinguished among 20 other users. Maybe I want to set k to 100. So this would increase a lot the number of these close points. So to conclude, we have a new method based on cryptography. We do not use any spatial transformation. And because of that, we have provable privacy guarantees. Why? Because nobody can stage any sort of attack based on, we have seen, data distribution, outliers, who knows what other heuristic, which some spatial cloaking methods may be vulnerable to. Of course, we still have the problem of cost. There is still room for improvement in terms of cost. We would like to have an even cheaper solution. And we would like to support more complex type of queries, not just nearest neighbors, right? This is also a very good direction for research. Okay, I will stop here if there are any questions. Thank you.
So, if anyone is interested in getting to know more and talking to Gabriel, he has an office in the CERIAS building across my office. Nearby the office. The second floor. So, and you can find his email address in the department web. So, this technique is quite fascinating.